This is Algebra Lesson 6-2, Solving Systems by Substitution. The substitution method is when one variable or expression is used in place of another. This method is very handy to use, especially when you can't graph something very easily. Graphing is great for solving systems of equations, but sometimes your solution doesn't land on a coordinate point, and it may be very difficult to interpret the fraction, or it doesn't intersect for quite a long time, and you don't have enough space to graph something that's way off your page. So another method for solving a system of equations is by substitution. By replacing one variable with an equivalent expression containing the other variable, you can create an equation that contains only one variable, and then we can solve it by the various methods that we used in Chapter 2. So we're going to talk about solving a system using substitution. Now, here I have two equations. Just like when I was graphing them, it is really a little bit easier to deal with these if we number them. So I'm going to number them equations 1 and equation 2. When you use substitution, you want to make your substitution as easy as possible. And the way you do that is you look at your equation and you find, I have two equations here, equation 1 and equation 2. If I look at equation 1, I see that it's already solved for y. Y is already set up to be equal to 3x. It would be much easier for me to substitute y into the second equation than it would be for me to substitute something from the second equation into the first equation. So whenever possible, if you have an equation that's solved for a single variable, that's the one you should key off of. So I can see here in equation 1 that y is equal to 3x. So now in equation 2, every time I see a y, I'm going to replace it with 3x. I'm going to substitute in 3x every time I see a y. So I'll have 2x plus 4 times y, but y is 3x, equals 28. So we substituted in 3x for y. Now I just need to solve this equation like normal because it's a single variable. So I have 2x plus 12x is equal to 28. So 14x is equal to 28. To solve this for x, I will divide by 14. So x is equal to 2. If x is equal to 2, now to solve for y, I'm going to plug 2 back into equation 1 because equation 1 is already solved for y. So in equation 1, I know that y equals 3 times x, but x is 2. So y is equal to 6. So the solution to this equation is 6. Now, while I could have graphed both of these, it seems like this is a little bit on the faster side. And it's definitely easier if you end up with equations that end up having answers that are fractions or that end up to be very large numbers. Let's look at problem number 2. If I look at problem number 2, again, I have two equations. I'm going to number them 1 and 2. Equation 1, x plus y equals 5. Equation 2, x equals y plus 1. Equation 2 is solved for a single variable. It's solved for x. So I'm going to take equation 2 and I'm going to substitute it into equation 1. That means every time in equation 1 that I see an x, I'm going to put in a y plus 1. So it says x, which is actually y plus 1, plus y is going to equal 5. All I did was substitute in this y plus 1 for that x right there. Now I can solve this. I have 2y plus 1 is equal to 5. Subtract 1. 2y is equal to 4. Divide by 2. Y is equal to 2. I know that y is equal to 2. In equation 2, I know that x is equal to y plus 1, so x is going to be equal to y, which is 2, plus 1. So that means that x is equal to 3. Remember, every time you solve an equation, you would need to answer the equation in a coordinate point. So the coordinate point is 3, 2. And again, you can always check these, just like we checked our other problems. We could plug in both of the numbers for x and y into both equations, and if they made both equations true, we would know that they worked. Now, sometimes you don't have an equation that's solved for a single variable. When this happens, one of your equations must be solved for a single variable. If we look at problem number 3 here, I have two equations. I'll aptly number them 1 and 2. Now, one of these equations is going to be much easier to solve for a single variable than the other. If I look at equation 1, I can see that 2x plus y equals 13. In this equation, there is no coefficient in front of y. Since there is no coefficient in front of y, it is going to be much easier for me to solve that equation for y than it would be to solve it for x, or to solve any for either variable in equation 2. So since equation 1 is already in a good position to solve for y, I'm just going to subtract 2x, so y will equal negative 2x plus 13. And if y equals negative 2x plus 13, in equation number 2, every time I see a y, I'm going to plug in negative 2x plus 13. So now that I know that y equals negative 2x plus 13, in equation 2, every time I see y, I'm going to substitute in negative 2x plus 13. So I have 4x minus 3 times y, which is negative 2x plus 13, is equal to 11. So 4x, let's simplify this. Distribute the negative 3. Negative 3 times negative 2x is positive 6x. And negative 3 times positive 13 is negative 39. And that's going to equal 11. 6 and 4 is 10, so 10x minus 39 equals 11. Add 39. 10x is equal to 50. Divide by 10. X is equal to 5. And now that I know that x is equal to 5, I'm going to plug it back into the equation that I solved for y, right up here, this one I just highlighted, because that's going to be easier for me. So I'm going to plug it into the adapted version of equation 1. So I'm going to have y equals negative 2 times 5 plus 13. That's negative 10 plus 13. So y is going to equal 3. So my solution to this equation is 5, 3. Let's look at problem number 4. Again, I have two equations. I'll number them 1 and 2. One of these will be much easier to solve for y than the other. If I look at this, I definitely don't want to solve either one of them for x, because if I'm going to solve them for x, I'm going to end up with fractions, which are really hard to deal with. Not impossible, but just harder to deal with. So I could solve equation 1 for y, or I could solve equation 2 for y. I think it would be easier to solve equation 2 for y, because the first equation has a negative y instead of a y. So I'm going to take equation 2, and I'm going to solve it for y. So y will equal, remember you're going to subtract your 2x, negative 2x plus 10. So now in equation 1, every time I see a y, I'm going to put in negative 2x plus 10. So I have 4x minus y, which is negative 2x plus 10. Be very careful with those signs. And that's going to equal 5. So now I'm going to distribute. Remember, if I distribute a negative, that means basically negative 1. So I will have 4x. Negative 1 times negative 2x is positive 2x. And negative 1 times positive 10 is negative 10 equals 5. So 4x plus 2x is 6x. 6x minus 10 equals 5. Add 10 to both sides. 6x equals 15. And you might be saying, but it doesn't divide evenly. That's okay. This is why substitution method is so handy, because sometimes you don't end up with whole numbers. Divide by 6 and reduce your fraction, obviously. 3 will go into 15 5 times. 3 goes into 6 twice. So my answer for that is 5 halves. Now to solve for y, I'm going to plug it into the adjusted version of equation 2. So I will have y equals negative 2 over 1 times 5 over 2 plus 10. Okay, these two 2's cancel out. So I have negative 1 times 5, which is negative 5. Negative 5 plus 10 is positive 5. So the solution to this equation is 5 halves 5. Or you could say 2 1/2 5. Either one works. I tend to leave mine as an improper fraction because if I'm going to plug it back in to check it, it's much easier to plug back in and check if it's an improper fraction. Now, you can also use substitution to solve a system of equations that are real-world equations. Okay? The most important thing is making sure you define your variables and making sure that you get your equations set up properly so you can solve them. So let's read this question. It says, the sum of a number and twice another number is 13. The first number is 4 larger than the second number. What are the numbers? I have a first number and a second number, so let's just let my variables equal first number and second number. So I'm going to let x equal my first number. And I'm going to let y equal my second number. So the sum of a number, that would be x. Sum means add. So my first equation is going to be the sum of a number and twice another number. So that would be twice the second number. Is means equals 13. There's my first equation. The first number is 4 larger than the second number. First number is. Okay, so first number is means x equals 4 larger than the second number. So the second number increased by 4. Okay, that's what the second equation says. The first number is 4 larger than the second number. Now, to solve this, I already have an equation that's set up for a single variable, so I'm going to substitute in y plus 4 into equation 1 every time I see an x. So in equation 1, every time I see an x, so x, which is y plus 4, plus 2y is equal to 13. 2y plus y is 3y. 3y plus 4 equals 13. Subtract 4. 3y equals 9. Divide by 3. Y is equal to 3. Which means in equation 2, x equals y, which is 3 plus 4. So x equals 7. Now you're not going to just say my numbers are 7 and 3. You're going to say the first number is 7 and the second number is 3 because that's how we defined them. Okay? So the answer would be the first number is 7 and the second number is 3. It's a real world problem, so you have to answer it in a sentence, interpreting what the coordinate point stood for. Always important to do that. Let's take a look at another equation. A youth group with 26 members is going to the beach. There will also be 5 chaperones that each will drive a van or a car. Each van seats 7 persons, including the driver. Each car seats 5 persons, including the driver. How many vans and cars will be needed? Now this one, we're going to base our variables off of the question that it's asking, and the question asking us is how many vans and how many cars do we need? So sometimes I find it easier for students, instead of using x and y, to actually use a variable that their brain can wrap their head around. So I'm going to use v for the number of vans. And I'm going to use c for the number of cars. Okay. So we have to come up with 2 equations. Okay. The first thing I'm going to do is I'm going to pay attention to the fact that it says there will also be 5 chaperones. If there are 5 chaperones, so if we pay attention to the sentence that says there will also be 5 chaperones that each will drive a van or a car, that means that that helps us to determine one of our equations. We cannot have more than 5 vans or cars total. So the number of vans plus the number of cars has to equal 5. That's one of our equations. So vans plus cars has to equal 5. The second equation is going to be based upon people. If there are 26 youth group members and also 5 chaperones, that means there's 31 total people. Right? Because if we have 26 members plus the 5 chaperones, that is 31 people. If each van can seat 7 and each car can seat 5, including the drivers, that means 7 people per van plus 5 people per car has to equal a total of 31 people. So 31 people have to get in those vehicles. So those are our 2 equations. So now I'm going to solve one of the equations for a specified variable. I'm going to choose equation 1, obviously, because v and c don't have any coefficients in front of them. And it doesn't matter if I solve it for v or I solve it for c. I'm going to solve it for v just because it's just as easy. So v equals negative c plus 5 if you move the c to the right-hand side. So in equation 2, every time I see a v, I'm going to put in a negative c plus 5. So 7 times v, which is negative c plus 5, plus 5c is equal to 31. Distribute the 7, that becomes negative 7c plus 35 plus 5c is equal to 31. Negative 7c plus 5c is negative 2c plus 35 is equal to 31. Subtract 35 and you will get negative 2c is equal to negative 4. Divide both sides by negative 2 and c equals 2. So there will be 2 cars. Going back to equation number 1, vans plus cars has to equal 5. So if we have vans plus cars having equal 5, or vans equals the opposite of c, which is negative 2 plus 5, so the number of vans has got to be 3. So they will need 3 vans and 2 cars. All right. The last thing we're going to talk about is, remember when you're solving a system, remember when we solved equations for a single variable, if we got a true statement like 2 equals 2 or 0 equals 0 or 3/4 equals 3/4, then that system had infinitely many solutions. And if we got a false statement like 6 equals 2, then the system had no solution. We can look at a system of equations and determine how many solutions it's going to have based upon solving that system. Because if we solve this system of equations and we get a true statement, then it's going to have infinitely many solutions. And if we solve that system and we get a false statement, it's going to have no solutions. So let's take a look at these 2 equations here. Okay, in the first equation, we have x minus is equal to negative 3y plus 4. And in the second equation, we have 6y plus 2x is equal to 8. Since the first equation is solved for x, I'm going to plug in negative 3y plus 4 every time I see an x in equation number 2. So I have 6y plus 2 times x, which is negative 3y plus 4, is equal to 8. So 6y plus, distributing my 2, that gives me negative 6y plus 6 is equal to 8. Well, 6y plus negative 6y cancels out, and I get 6 equals 8, which is a false statement because 6 does not equal 8. Since that is a false statement, oh, I messed up. Back up, back up, back up. 2 times 3 is 6, but 2 times 4 is 8. I just realized what I did. So back up here, we should have had negative 6y plus 8. We get 8 equals 8 instead of 6 equals 8, which is a true statement. 8 is definitely equal to 8. And since 8 is equal to 8, this means this system is going to have infinitely many solutions. And of course, we should name the line. So I could name either one of the lines, but it has infinitely many solutions on 6y plus 2x equals 8. In this second equation here, second or eighth problem, which I have my two equations, my first equation says y equals 4x minus 9, and my second equation says y minus 4x equals 6. So I'm going to plug in 4x minus 9 everywhere I see a y, which is right there in equation 2. So I'm going to have 4x minus 9 minus 4x equals 6. So my two 4x's cancel out, and I get negative 9 equals 6, which is not true. Since negative 9 does not equal 6, this would have no solution, because it is a false statement. So you can clearly see that solving systems by substitution is just another way of being able to solve them. Much nicer than graphing in some instances. Sometimes graphing will be more helpful. Sometimes you can only graph. Later on this chapter, you'll learn what situations in which you have to solve a system by graphing. All right. But right now, this is another method to solving a system of equations. All right, our closure question for today. What is a good situation for using the substitution method? What is a difficult situation for using the substitution method? Please answer both of those questions. What is a good setup? In other words, when is it easy to solve by substitution? When is it not quite as easy to solve by substitution? Basically, that's what that question is asking.